All right, good evening, class. So shall we start? All right, so we are coming to the end of this course. So this will be the last class, right, on a new topic. But next week we will still have one class, but that will be just revision of the knowledge we have learned. So today will be the last class for a new subject. Okay. So what we have learned so far. So the core of this part 2, right, is about how to improve the performance of the system. Okay. We say, okay, want to control, which means we want to improve, right, the performance of the system. You are not satisfied with the performance of current system. You want to do something, right? You want to do something, and the fundamental principle behind the control systems is the feedback. So you want to change the behavior of the system, right? You monitor the output, so you can observe. So when we say output, that is something we can see, we can observe, we can measure. So it is something we know. Okay, and then we feedback means we are going to use the information we observe. So we have to measure. And then there is a desired performance reference. So that's the desired output you want the system to have. Therefore, you compare with the desired one, then you get an error signal. And the purpose of this controller is try to minimize this error signal. So you will do the measure, we compare, and then we do the correction. That is what we call the feedback. Okay, and the purpose, right, we try to make this output, actual output of the system, follow the desired output as close as possible. Okay. Then there are a number of questions. The first one is, how are we going to specify the reference signal with the desired output? Right. For that one, we say, oh, okay, in practical control problems, normally you will be given some performance requirements, right? You want the system to satisfy. And because we have a perfect knowledge about the step response of a second order system, so a very common practice is that we use this second order model as the reference model. Okay, and we know, okay, this is the transfer function of the second order system, which is essentially just a damped oscillator. Right? We have the damping ratio and natural frequency, so everything will be described by those two parameters. All right. Okay. Here, right. I think this one. Let's talk about the overshoot. Overshoot. Since you are doing the project, of course, some students ask me, you know, before it overshoot, probably it undershoot, right? Something like that. Finally, if that happens, right, we just consider the one which is overshoot, the first peak after it is go over the final value, right? Everything under that, we don't consider those as overshoot, overshoot. So therefore, whatever happens, right, as long as it does not become bigger than the final value, right, we say the overshoot will be 0. Okay. So of course, sometimes you say, okay, if you know the output is here, right, probably is over there, right? Negative. Of course, you will say, okay, whatever happens, but overshoot has to be below that negative value. The magnitude, right? We're talking about this one. Is that clear? That is how you compute the overshoot for your MIDI project. Your MIDI project, the system is very complex, right? It's a 6-order system. You know, the transient behavior will look very strange, right? You compare to this. This is a standard 2nd-order system. Okay. All right. So But anyway, let's go back to this, this second order system. We have a perfect knowledge, if we talk about overshoot, we know, okay, this overshoot ratio is related to the damping ratio, right? We have this formula. And then we also, if we talk about the 2% settling time, right? Then we also have a formula. If we talk about the rise time, then we have another formula, okay? Of course, when you do your mini project, if there is no overshoot, which I think the overshoot ratio, is below 10%, right? If there is no overshoot, of course, it satisfies the requirement. Okay. Okay, you have those requirements, so you figure out what are the appropriate values of the damping ratio natural frequency such that it can meet all the requirements on the damping ratio and on the overshoot and the settling time or the rise time. Then you build the reference model. From that reference model, of course, then we will get the desired pose. Okay. Of course, for your mini project, there are it's a 6 order system. You have to place the other poles, right? There are 4 more poles to place. Then you place all those poles far away from the dominant one. But of course, for the dominant one, right? For the dominant one, you do something and then there are a number of factors. Okay, it depends upon how what kind of method you place the poles, right? Even you have the you place the poles to the same position, but different method will give you a different result. Normally, the 4-rank method, right, because it can explore all the control signals, most of the time it can give you the better result. Okay, and also if everything fails, then you have to change the position of the poles, right? You have to design other position of the poles. Normally, of course, it's the dominant poles that matters. Okay, the 2 factors, right? Dominant poles and also the way the method you use to solve the pole placement problem. Okay. Because one student sent me email, he could not meet the requirements, right? By pole placement, or somehow said you have to change, the way. And later he replied, he sent me email saying he did it. So he just changed the way the method he used for the pole placement. So he changed his original one to the 4-rank method, and also changed the way to specify the desired controllable kinetic force. Okay, so those are the tips I want to share with you, which can help you. The point is that with the proper way, right, all the performance requirements can be met, using the pole placement method for your mini project. Okay, now here we say, okay, from the performance requirements, you design the positions of the poles. Then, of course, the first type of controller we introduce are the pole placement, right? Pole placement. And what kind of form does the controller take? This one you are very familiar now, right? Okay. So although I put a F here, but for pole placement, right, normally those F is just an identity matrix. Right, F will come into play when you try to do the decoupling. So, so therefore, when you do the pole placement, right, this F is R. So it's essentially just minus Kx plus R. And there are, many possible poles to meet the performance requirements. And very often we want to choose the best one to strike the balance between the speed and the cost. That's the motivation for the second controller we have studied, right? The optimal control. Now, does the optimal controller right, take the same form as that for the pole placement? Right. Actually, it also has the same form. The only difference is the way you compute this gain matrix. Okay. So this time you need to solve this algebraic Riccati equation. Okay, I think that also I made it clear in the class, to get the proper design which can meet the performance requirements. There are a number of experiments that will be involved, right? You want to find out the basically that's the weighting matrix that will matter. In this LQR design, the design parameters are those Q and R, right? Q and R, it will take some time. And for each Q and R, if you do it by hand, of course, I mean, it is quite tedious, right? For that matters, you can use some of the, I think there's the LQR in the control system toolbox, so we can use that to speed up the search time. But when you, let's say, finally you find something that works, right? You find the problem value of Q and R. For that final answer, you have to give me the whole calculation procedure, right? Okay, like you say, okay, I think this one, you are not going to solve this ARE equation directly, right? There are two ways, right? One is to do it directly. That one will not work out because this is a 6th order system. It's very complicated, right? You have to use the eigenvector method, right? You have to get a 12 by 12 matrix, right? And then, of course, then you can get the eigenvectors, right? And then for those, stable eigenvalues, you get those eigenvectors, you put them, and then use the formula to get the P matrix. Okay, so you have to go through that procedure to do it. For the final answer, final design, you have to give me the whole calculation procedure. Okay, is that clear? You cannot just, okay, I use LQR to get the answer, right? If you do that, well, you are going to lose a lot of marks because that doesn't show me how you understand the whole design. Okay. All right. After the power placement of the optimal controller, right? What type of controller did we discuss? For the purpose of this power placement optimal, right? You try to drive the output to some constant or to a equivalent position, right? But normally, for many control systems, we want the output to follow something, right? Some constant or a time varying signal. So that's the purpose of the servo control, right? We try to follow a desired output. That desired output may not be a constant, maybe a time varying signal, maybe a sinusoid. And also we want to deal with the disturbance. Okay. How many ways to design the servo control? We have learned, right? We introduced two ways. We either use state feedback or use output feedback. Now, for the servo control, does the state feedback controller takes the same form as this? Okay, not exactly, but it's very similar, right? It's just we have to change the state vector, right? We have to change X to an augmented state. X bar, right? X bar equal to the state X, and also that is the error signal, right? The integrator of the error signal. So we say when you design those K, right, you can use LQR or use the power placement to make the whole system stable. So that's why you have to know how to stabilize the whole system, right? But also, so we introduce this integrator. That is the secret, right, to deal with the constant output. We want to, if you want the output to track a constant with zero steady state error, okay, then we need to use the integrator. Okay, and then that is what we call the servo mechanism. But you want to solve the problem for the servo control, right? You have to have a proper servo mechanism in addition to stabilization. Okay. In this class, right, for the multiple input, multiple output system, we only introduce the way to deal with the constant reference output. But I also mentioned, right, for other types of output, like the sinusoid, there are ways to deal with that, right? We don't have time to cover that. But remember, those problems are already solved. You don't say, okay, there are some open questions you want to solve in that direction. No, there are standard ways to do it. So after servo control, there is another controller we discussed, right? That is a unique feature for the multiple input, multiple output, right? It's called decoupling. Okay. Now, the motivation for decoupling, of course, is very different from the motivation for power placement or for optimal control, right? This is just for easy operation. Let's say you have two output, you want to control it with two reference input, and then for easy operation, okay, you say, I want to change one output, right? Then what I want to do is I just change one input. Then that's the way, okay, the system is decoupled, you can do that. Okay, it's basically, you say, okay, there are two outputs, right? For one output, I only need to change one reference input to change that. The other output will keep it the same. Then the decoupling can achieve that. If you don't use decoupling, it will be more complicated, right? To do it. If you change one input, both outputs will be affected without decoupling. Okay, so how many ways for decoupling? We have introduced two ways, right? State feedback and output feedback. Those two ways are two different methods, right? And also those two different methods are not equivalent to each other, right? If you found out one method may not work, but probably the other method may work. Okay. For the state feedback, it also takes the same form. Okay, now here, the purpose to introduce those if is for decoupling. All right. So let's summarize what we have learned, right? For linear, if the system is linear, right, actually we can meet almost any performance requirement if there is no limit on the magnitude of the control input we can apply. So in theory, because we never mention how big, what is the maximum value of the input we can apply, right? We never consider those constraints. When we say it is stable, we just say it will not blow up to infinity, right? But in that process, the required control input may be huge, right? But we didn't consider whether there is a cap, right, on those values. Okay, but if, right, we say if there is no limit on the control input we can apply, actually indeed we can, control the system to meet any performance requirements we like. Of course, in reality, there is always a limit, right? In theory, you can do it. In reality, there is a limit. And the most commonly used controller is the state feedback controller. Okay, the state feedback controller has advantage to deal with the multiple input, multiple output system. We know for multiple input, multiple output, it's not straightforward to deal with it with the transfer function. Okay, but let's take a close look at the feedback control, right, and say what are the problems. In theory, right, this type of controller can meet almost any performance requirements we like. But how are we going to implement that? If we look at the mathematical form, right, it says, okay, to compute the input, we require the information about X, right? We need the state vector. Of course, the reference input, that one is not a problem. R, of course, because you know what is the reference input, right? You have a desired output in your mind. Okay, this one, we need to know all the state variables to make it work, right? So in terms of implementation, means that we need to have for the sensors to measure all the state variables. Okay, imagine if the system consists of a lot of state variables, right? You may have some issues. The first direct one is that maybe, right, not all the state variables can be measured. Okay, and even if all the state variables can be measured, probably you don't have the budget to buy the sensor to measure some of the state variables. Maybe it's too expensive to measure, right? Okay. So therefore, the state estimation today we're going to talk about is about how we save money. We don't need to measure all the state variables. Okay. There is no need to put the sensor to measure all the state variables because the state variables are connected with each other. Okay, for those expensive ones or unaccessible ones, we can just try to estimate them. This subject of the state estimation, of course, is not only useful for control system design, it is also useful for other applications, right, like signal processing and sensor fusion. In reality, actually, you are going to encounter some problems. Look, you say, I want to measure something. Okay, which means you want to know the signals, right? After learning today's topic, then you will know you don't have to measure it directly. Okay, you don't have to buy sensors to do that. There are some other ways to do it, probably which are also as good as the one you use a sensor to measure. Okay. All right. So let's recap. Right. What I've discussed. We say, okay, look, we want to use the state feedback, but we cannot measure all the state variables. Okay. On the output is measurable. Okay. Remember, whenever we say, right, this is the output, means that signal you can observe, right? You can observe, you can measure it. If you cannot observe directly, we never call it output. All right. So therefore, we can only use the output information, but we don't have the state, so we have to estimate that, right? Otherwise, we cannot use this type of control. Okay, so we have to estimate the state. And why we can estimate that? Because if we know some of the state information, actually, we can construct all the state variables because they are connected with each other, right? We have the mathematical model which can help us. So it's in short, if you want to know something, remember, you also actually, that's a good lesson. You can either observe it, you can either say it directly or you can infer it, right? Indirectly. All right. Let's take an industrial example like this. We talk about the distillation column in the refinery industry, right? We saw those huge towers in the chemical factory. Those towers actually contains a lot of plates. For those plates, right, the temperatures are different. Those are the state variables. But normally, we only need to measure the top plate and the bottom one. We don't have to put sensors to measure the temperatures at all the levels. Okay. Then there is another industrial motivation is about copper tank. Okay, here I have a short video clip for copper tank. This is you will see many of the copper tank that are connected. the liquid from tank 1 will flow into tank 2, depending on the level. So so liquid can flow in. So you have a pump, you can control the flow rate to the first tank. There is a pump, you can control the flow rate, which is flow out of the second tank, right? This first tank and the second tank, they are connected at the bottom, so the liquid can flow from the first tank to the second tank. Okay, and those flow rates will be the input, and the two water levels, H1, H2, they are the state variables. That's something observed for this problem, right? We say, okay, we are interested in looking at the levels of those of the liquid in those two tanks. But let's say you can only afford one sensor. You can only afford one sensor to measure the level of the second tank, right? You don't have the two sensors to measure both H1 and H2. You can only measure H2. How do we get the level for the first tank? You see, if you can do it, right, which means actually you can save money, right? You can save the money to buy a sensor to measure the tank of the first one. Okay, for this type of problem, of course, always, right, you want to estimate something, you have to have the model, right? If you don't have the model, we cannot do it. So the height of the liquid in the tank 1, of course, you say this F1 as flow rate flow in, you know, F12, that's the flow rate which runs from the tank 1 to tank 2, right? So it's F1 minus F12. So the change rate of the second one is the you know, the water flow from the tank 1 to second tank, right? F12 minus F2, that's the flow rate outflow rate of the second tank. So you have those two equations. H1 and H2, they are the water level. F1 and F2, they are the input. Of course, then how about F12? So from mechanics, fluid mechanics, okay, there is a formula related describing the F12. They are related to the difference of the water level. Okay, in this way. Okay, and then after some, of course, we need to use our linear model. So we will do some linearization. I will skip the details. So eventually, you have a linear model. Okay, after linearization, you get a linear model. So it's a second order system. So delta H1, delta H2, they are the water levels. They are the state variable, and F1, F2 are the input. So so therefore, after that, we have a standard linear system, right? ABC. So okay, and ABC is 0, 1 because we only know the water level of the second tank, right? Okay, so you know this. So we only have the information about the output. How are we going to get the information about the whole state vector, which include the both H1 and H2? That is the problem we are going to solve. But of course, right now we don't know the answer, so we are going to give you the general solution first, and then we'll come back to give the solution for this problem. Okay. Okay, now let's pose the state estimation problem in a mathematical way. Now we know the model, right? ABC. The problem is that we want to estimate the state vector, and what we know, of course, we know the output Y. We know the input signals, right? Of course, we know the output and the input. We want to estimate the state vector. Then, of course, there are many questions. First of all, is it possible? The second one, if it's possible, then how are we going to estimate? Okay, Then first we will try to recall what we have learned about observability, right? Probably the observability metrics that can help us. From that angle, we can come up with a very simple way. One way will be like this. We know the output signal y, so let's take the derivative. So y dot will be c x dot. Therefore, but we know x dot, right, is related to x and u, right? We plug it in, so we have cx plus cp ut. So therefore, okay, then we have an equation relating the y dot and x, right? Now is cax plus cb. Then we take the derivative on both sides again, right? Therefore, we have double dot, but this time, right, we have the cax dot, and then we plug in the expression of x dot again, right? So eventually, so you will get something like this. Let's say we take the derivative n-1 times of the output. We are going to relate this one to the x, right? And also some other terms. Here we have the c, right? The y dot will have our cax, this one, right? Then this is ca to the power of n-1x. And then all other signals will be related to the input. Okay, so if we reorganize those equations, actually we'll end up with an equation like this. The first one say x, right, corresponding to y. The second one say ax, well, we corresponding to y dot, and also something, cpu. Okay, and then there's some, okay, finally they say a to the power n-1, right? This times x, right, we relate to the n-1 derivative of y, okay, and other signals related to the input and output. So you can say we have an equation. If a system is observable, you look at this matrix, right? You should realize that is the observability matrix, right? You have learned, we say, okay, it has to be 4 rank such that system is observable. We say, okay, if this matrix is 4 rank, you can't solve the equation to get x. Therefore, in theory, we can't get the state vector, right, from the information on the input and output. But nobody uses in practice to estimate the state vectors in this way. Okay, there is a good reason for that. There are some signals which is, if you use this way, there are some signals which can't give us trouble. Okay, if you look at those signals, y dot, and the u input, which signal might give us trouble? If you have any sense, right, signal processing, which signal may give us some headache? Is about y or the derivative of the output or the input? It is always dangerous to differentiate a signal, right? Because there is a noise in the signal. The main output invariably involves noise, right? I know the noise normally that the high frequency signal, okay? And what happens if you take a derivative with a high frequency signal, right? Even the signal itself is with no magnitude, but if you take a derivative, right? If you take a derivative, that will make the value huge. that will corrupt your estimation, right? Is that clear? So always, right, from signal process, we know you normally you want to avoid the usage of a differentiation of something because it can magnify the noise. The differentiation operation will magnify the noise. That's not what we want, right? Okay, so we don't want to use the derivatives of the output. Is that clear? Therefore, we have to find some other ways. All right, then let's think about that. Okay, probably there is another simple way, or we call it a naive way. That, okay, because we already know the model, right? ABC. The only thing that we don't know X. So hey, okay, I can just put another model. I know the ABC, you know, I want the simulator, but I just replace X by X height, right? We say X height is the estimation, right? And then, so therefore this is the system, okay? And then this is your estimator, is a exact copy of your system, but the only thing is, right? You may not know the initial condition, right? But remember, if those two have the initial condition, if the X height with the same initial condition as the state, of course, right, the X height will be equal to X start at the beginning, right? Mathematically, you have the same equation with the same initial condition. You have the same solution. But of course, the only problem is that, do we know the initial state? Do we know the initial state? We don't know the initial state, right? What we know is the output. We don't have the information for the whole state vector. Okay? Okay. Then we have to idealize. So what if the initial state, you know, they are different? We want to idealize, you know, what happens to the estimation error. We want estimation error go to zero, right? Go to zero, we say it may not be the same at the beginning, but eventually we want the estimation error X tilde converge to zero. Okay, then we need to write down, right? We have to, whenever you encounter this equation, of course, you have to write down the equation for the error rate, right? The change rate is, it means that you have to get the derivative of the X tilde. Right? Of course, we have the equation for X, have the equation for X height. It's very easy for you to get the equation for the change rate of X tilde, right? So AX plus BU minus AX height plus BU cancel out, we get A times X tilde, a very simple equation. Now, if you look at this equation, so from what you have learned in this course, it should be very clear to you that when will the X tilde go to zero. So we know we don't have the initial state. That's why we cannot make the X height equals X. What we hope, right, is the X height will converge to X when time t goes to infinity. Of course, if we look at the estimation, the dynamics of the estimation error, we know that can happen, right, if the A is stable, right? X height tilde will go to zero. But what happens if A is unstable? If A is unstable, what is the X tilde? Well, does it blow up or go to zero? It will blow up, right? It will increase exponentially. So your estimation error will blow up, right? You have no confidence about your estimated state variable. Okay, so we have to overcome this problem. Therefore, we have to do something more in addition to make a copy of the original system, right? Okay, so what we have learned, what we have observed is We want to estimate x, right? Of course, we don't know the x. Even we don't know the initial state. Okay, if we know the initial state, it is simple. And we don't know the initial state, then the state estimation error is expected. Okay. Therefore, we have to correct. We have to have some correction mechanism for, and we want the estimation to be corrected in such a way that an error will go to, the estimation error will go to 0 at the end. The state estimation error itself, of course, is not available, right? We don't know the state. We don't know the x tilde, the estimation error. What we know is the output information, right? So we know that we measure the real output of the system, and the estimator will also give me the estimated output. Okay, y height is z times x height. So this one we know we can compute. We also measure the output itself, and the difference between those two, we can use that information to correct the estimation. So therefore, we may correct and reduce the error in the estimation by using some feedback, and this feedback information will come from the output y and the estimated output y height. Okay, therefore let's say output you can measure, right? This y height you can compute from your estimation algorithm, and we want to use the difference of those two signals. And what is the simplest way to use this estimation error? What is the simplest controller you have studied? Proportional control, right? So the simplest way to use this error is that make it proportional. You make it correction, right? Proportional to the estimation error. Okay. So always try the simplest way, right? To make it work. Make it proportional. We want to add this correction to the model and see whether that can help us. Okay, so that's the idea of the 4-order observer. Of course, this was proposed a long time ago, right? Almost 60 years ago. This is the system. So this is the model of the system, right? ABC with the same thing, but we add a feedback. This is the actual output which we can measure, right? This is the estimated output. We take the difference, right? And then we make it proportional. The correction is proportional to this output error to the model. And then you're going to say, finally, it works. So the observer is the system model plus the feedback correction. You can say there are two components. We need to know the model of the system, right? And we need to have some kind of feedback mechanism. Now, the objective of the observer is that we want to make the x height converge to x when time goes to infinity. And we want to make the change rate of the error, right, to be adjustable. So we can make it quicker, we can make it slower. Then let's do the mathematical analysis of the observer. So this is the model of the system, right? We build our observer. You look at the mathematical form. Without this feedback, right, it's just a copy of the original model, right? We know that may not work when A is unstable. Now we add a correction, right? We add a correction to this equation. Okay, and hopefully it can achieve the goal. Okay, then of course we have to analyze the dynamics of the estimation error, right? We want to see how the feedback can help to make the error signal go to 0. So again, let's define the estimation error x tilde as x minus x height. Then we have to compute its derivative, right? X tilde dot x dot minus x height dot, but x dot is ax plus bu, x height dot is ax height plus bu plus the correction. And then bu will be cancelled out. So we get ax minus x height, right? And minus air. Here, this y. Here, output window is related to x, right? By cx. So we use cx here minus, this is cx height. Okay, now we take out this c. Take out the c, and this just becomes x minus x height. And then we group, right, those two together. We have the x tilde dot equals a minus lc times x tilde. Okay. Now, without the feedback, right, the original estimation error equation is just x tilde equals x tilde dot equals a times x tilde, right? Without the feedback, we know it doesn't work when a is unstable. But here we say, okay, we have some help. We can change error. We can change error. Okay, if we choose error such that this matrix A minus R times C, right? A minus R times C. This matrix is stable. Then we can make this x tilde go to 0. So what is important is the new matrix, right, which can be changed by R, right? A minus R C. Okay. So if we can design R to make this matrix A minus R C to be stable, then the problem is solved. Okay, in this design, we know we didn't use any derivatives of the output signal, right, in the observer. And also this estimation error, the change rate of the estimation error can be adjusted by error. Okay, now let's take a close look at this equation. Even when this A is unstable, right, we can design R to make this A minus LC stable. That will solve the problem. So no matter, it doesn't matter whether the original system is stable or not, we can always estimate the state value. Of course, naturally, then the question, the mathematical question is, right, is when can we make this matrix A minus AC to be stable? Or even further, can we place the eigenvalues of this A minus AC to be any stable eigenvalues as we like? All right, for that purpose, right, let's analyze its characteristic polynomial of this matrix. Characteristic polynomial, of course, that's the determinant of this matrix, right? Si minus A minus LC. Okay, now there is a trick. Here is an important operation. Okay, that can relate the design problem of this observer to the old problem we have solved. Okay, here we say, okay, this is the design matrix, right? Air. I want to make this air appears on the right side, and we know, okay, the determinant of this matrix, right, will be the same as the determinant of the transpose of that matrix. If the matrix is a square matrix, right? Square matrix, you can do that. All right. Okay. Then we take the transpose of this matrix. This A transpose LC, right? We do the transpose of LC, of course, becomes the C transpose times L transpose. That can change the order of the multiplication when we do the transpose. Remember, that's a very important property of the transpose operation. Okay, in this way, then let's just make the final form to be recognizable by you. Okay, let's say, okay, this, I'm going to use A tilde to denote A transpose. Okay, A tilde corresponds to A transpose. B tilde corresponding to C transpose. K tilde corresponding to L transpose. Therefore, the question is, given a pair of matrix A tilde and B tilde, right? A and C are given, so A tilde and B tilde are alone. Can we find K tilde such that A tilde minus B tilde times K tilde is stable? You look at the way we define the problem. Have we solved this problem in the past? That is the problem I solved in the first class, right? Chapter 7. You are given A, right? Matrix A, you are given the control vector B, right? And then you are trying to find a matrix K to be the A minus PK. The pose of the A minus PK to anywhere we like. And then you know how to do it. Okay? So we already solved this problem, right? So the observer design problem is just a power placement problem. Also, we know, by duality, right? This, we have learned that. We say if the pair AC is observable, it means this pair, right? A transpose C transpose is controllable. So this is the time we can use it, such that we know, if we know how to solve the power placement problem of controller, then we know the solution for the observer design. Okay, if AC is observable, means A tilde, B tilde is controllable, right? We can place the pose to anywhere we like. In other words, when L can be found, place the roots of this characteristic polynomial of A minus LC to be anywhere we like. And you can apply all the methods discussed in chapter 7, right? Okay. If the system is only one input and one output, means okay, there is only one output, then you can use the SISO method, right? Equivalence formula, or you can use direct comparison. If there are multiple outputs, means there are multiple input, right? Then you can use either the unity rank or the full rank method. Okay, so you can do it with whatever you prefer to solve the observer design problem. Okay, but before we solve the problem, we need to know how we design the desired position of the desired pose, right? So where should we place the pose of the observer? Then let's recall, how did we design the desired pose of the controller? We say we have to look at the performance requirements, right? We'll look at the overshoot ratio, we'll look at the settling time, right? Then we figure out the corresponding second order system, right? We design the other pose. So basically, we have to look at the performance requirements, but that is for the controller. But Can we use the same performance requirements to design the pose for observer? Then you have to think, what is objective of the observer? We try to estimate the state variable, right? Do we expect that those state variables, the estimated state variables, to satisfy the requirements on the damping ratio or on the overshoot or the settling time? What we really like is that we want the estimation to go to 0 as fast as possible, right? We want the estimation to be accurate as possible and to be very fast. So for observer, what we care is how fast the estimation error will go to 0, right? We want to be fast and accurate. Well, then let's take a look at the aerodynamics and say, what kind of design will make this X2 go to 0 very fast? If you look at this equation, just to simplify the matter, right? Imagine X2 is a scalar, right? Is a scalar. So what kind of design can make the X2 go to 0 very fast? You want to choose a big L or small L. Of course, you want to use a very big L, right? It's very negative. Then it will go to 0 very fast. So it appears, right? I mean, because if you look at this equation, the rate of convergence to 0 of this X2, of course, will be controlled by how negative the real parts of the pose of the observer is very far away from the origin. It will go to 0 very fast. Therefore, if you want to be very fast, by simply looking at this equation, it appears we just choose a very large gain, right? Very big. So it means the higher gain, the better. But then there is a catch. So it may not be as simple as you think, because again, we have to consider the effect of the noise. Okay? Because the observation has been always, right, there has been a noise associated with your observation. So therefore, y is Cx and plus d. D is the observation noise, right? If we plug in this expression into the equation, then actually easily we can get the equation for the estimation error. This estimation error, X2, not only depends upon X2, also depends upon the observation noise. Okay. Now you just look at this equation. You will realize, right? You will realize there may be some issue when air is big, right? When air is big, this term, ALD will be big. Without D, of course, X2 will go to 0, right? But this is the equation, right? It's a stable system, but there is some external input. You can treat it as some kind of disturbance, right? Or noise. And that will affect X2. A large error will lead to large estimation error if D is persistent. Okay. Then you can say there must be a trade-off in achieving small error, right? We know large error may be needed for fast convergence if there is no noise. But on the other hand, we know a small error will minimize the impact of the noise. So we cannot make it too big, but we don't want to be too small. Right? Then, so this trade-off actually can be formulated as optimization problem. Right? That's why the Kalman filter was introduced to optimize the observer design. The key difference between the observer we have shown you, right? Between that observer and the common filter is just the gain. In the current design, the error is a constant gain. But for common filter, right, the error will be a time variable. Well, depends on there will be an algorithm. Right? Common filter, there's the algorithm for you to compute the gain. And that gain is not a constant. Okay. But of course, we don't have time to cover the common filter. It's out of the scope of this module. Instead, so for this module, we say, okay, we just use a very simple empirical rule. The observer designs to find a suitable observer gain error, right, matrix. Then we can use the power placement to adjust the rate of the convergence of the x height to x. We know that the observer gain pose, right? The choice of the observer pose is a trade-off between the speed and the constraint imposed by noise, saturation, and nonlinearity. Okay, here is a simple guideline. Let's say for this module or for this course, we use this simple rule. We just place the observer pose 3 to 5 times faster than the closed loop dominant pose designed by the controller. For the controller design, you already know the dominant pose, right, of the closed loop. So for the observer design, you place in them faster than the pose for the control system. Okay, 3 to 5 times faster. These are some just a good rule for the from the experience in the control system design. But of course, for real world applications, remember when you try to estimate the state variable, common filter is the most popular way and also effective way. Okay, so in reality, if you want to do the state estimation, you should learn common filter to do it. Here, this course, right, this observer design, of course, I actually give you some kind of good motivation or the kind of introduction about the mathematical form of the observer. Okay, let's summarize the design procedure. We know it's a power placement problem, right? So first, you choose the desired pose for the observer, 3 to 5 times faster than the controller pose. Okay, you can use this as a guideline when you do the project for your mini project. Okay, then you use a power placement algorithm to obtain error. Okay, and of course, when you do this, let's say for mini project is a multiple input, multiple output system. Then there are many ways to solve that. Then you implement the observer. So this, remember, when we talk about the observer, this is the equation with algorithm for the observer. You have to write down, okay, A, B, and error. There is a feedback term in this equation. Okay, in the past, there are a mistake made by the students. You say, okay, I designed the observer. So what the students did, they didn't write down the equation for this observer. They just give me the answer for error. That, of course, you are going to lose some marks if you don't write down the equation, right? You just give me the error. I ask you for your observer. You give me the answer of error. So I don't know what's the meaning of your error. Okay, so you have to give me the complete answer. Okay. Now let's look at an example. A very simple example: a second order system, right? Second order system. So actually, this is a controllable canonic form. But this one, for the observer design, right, we don't care about whether it's controllable or not. We have to test whether it's observable or not. So it can be easily checked. the observability matrix C, C, A, right? This is C, this is C times A. Of course, it's a non-singular. Okay, how going to solve the power placement? Because this one, there is only one output. So, and also in second order, right, we can just use direct comparison. We use a direct comparison, which means, right, you compute this matrix A minus LC, right? This is A, this is L, this is C. You get this matrix, and then you get the characteristic polynomial of this matrix, which is the determinant of lambda I, identity matrix minus A, right? You get this one. So what comes lambda plus L1, right? This is minus 1. Now here minus L2 becomes L2. Here 0 becomes lambda minus 0. You get the determinant of this matrix, right? You get this one. Okay, so that is the correct polynomial of the observer. Okay, let's say you place the pose of the observer, right, to somewhere. Okay, let's say I give you the pose, then you just place the pose to those positions, right? Your build project, you know, okay, you design the pose to be 3 to 5 times faster. Of course, in some problem, if you are not given the pose, you design the stable pose by yourself, right? You choose some simple numbers, right? But always remember, you have to give me the stable pose when you do the power placement problem. You don't say, okay, you want to make it simple. You put the pose, let's say, at 0. You want to make it simple. You want to put the pose at 0, right? You don't try those funny things. You put the pose as 1. Okay, that will cause you a lot of trouble. After this whole course, and then you give me some unstable system, right? That you miss some of the critical part of this control system theory. Has to be, everything has to be stable. Okay, so therefore you here you get lambda file, you put it in, then you get your design of L1 and L2. So finally, you say, okay, this is the observer. Okay. Of course, let's say in your final exam, you don't have to write down in this way, right? As long as you give me, okay, x height equals ax height plus bu, right? And you already define your a and b, so it is fine, right? You don't have to write all those values, right? Here, but at least show me the equation, for your observer. Okay, here, okay, and also I do one more step, right? I will merge this y here, because y is cx, right? I merge this part into this matrix. That's how I obtain the equation for this observer in a different form, right? It's just say, okay, this x height dot equals something times x height plus something times u, right? Plus something times the output. Okay, they are the same. Okay, let's do the simulation. So here I already show you this, the block diagram, right? At this moment, I think most of you have already practiced how to use the Simulink to build those block diagrams. It's very easy. On Simulink, you have all those blocks, you have the integrator, you have the scans in there. You just put them together, build a block diagram and do the simulation. Okay, here we say actually that system itself is just a double integrator, right? You have this is output, is x1. You try to estimate both x1 and x2, right? You reconstruct that. But then, if you look at the observer, right here, from this observer, I can give you the estimation of both x1 and x2. But remember, the output itself, right, is x1. Therefore, do we need to estimate x1? From the observer, it will give you the x1 height, right? That's the estimation of x1. But in reality, right, probably you are not going to use x1 height, you are going to use the output, because the output signal is the first state variable. Okay, so therefore that is also one of the issue with that four order observer, right? We try to estimate all the state variables, but x1 actually is already available through the output itself. There is no need to reconstruct that. In fact, we only need to estimate x2. So that implies this observer, has some redundancy information in the model. Probably we only need to build an observer which is a first order system instead of a second order system. So it is this observation that leads to the investigation of lower order observers. And we are going to discuss that later. We're going to resolve this issue later. Okay, now let's go back to the industrial applications, the copper tank level estimation. Now, at the beginning, I said, okay, I just have the sensor to measure the tank, the water level of the second tank, right? So the output is x2. Now, I want to estimate x1. That is our observer design problem, right? We want to estimate the state variables. Here you are given the ABC, so it's very easy to design the observer. We need to estimate x1. So therefore, we design the observer in a very simple way. We use AB and also a feedback again in the observer. Okay, and again, because this one is a second order system, it's very easy to do it with a direct comparison. Okay, so we do it with direct comparison. I think for your mini project, the sixth order also is multiple output. You may also use the full rank method. Okay, this one, right, we get the E minus LC, we get the correct polynomial of this matrix, right? We end up with this equation. Okay, and then of course we want to match this with a desired correct polynomial. For that purpose, right, we need to know the desired pose. Okay, remember also, here I just want two simple pose, lambda equals -1. Because of course, -1 is a very simple number, right? If you are not given the desired pose, you can always use some simple number like -1. Okay, so you use -1, you put it in, right, and then you compare the coefficients, you will get your design for L1 and L2 here. So finally, this will be the observer. So the observer is an equation involves the x height, right? It depends upon the input, depends upon the output. And this is this is simulation, right? We can say, how good is your estimation? This is the result when the initial state is 0.5 and 0.34, right? The sign corresponding to the actual state variable, right? And of course, at the beginning, we don't know the initial state. We can make the initial state to be 0. Even though that the estimated value at 0, we know at the beginning, of course, does not match the actual value. But as time goes on, right, after a while, after about 3 seconds, right, it is very close to the true value. Okay, that serves the purpose of the observer. Okay, I think the solution to the observer design, right, is quite simple. It's just a power placement problem. Right? Okay. All right. So with that, I will call the break, right, and then let's have 15 minutes break, and then we will continue to the second half. All right, welcome back. All right, let's continue. Now we just discussed how we estimate the state variable, right? And then we want to understand, right? What happens if we use the estimated state instead of the true state? We want to analyze the performance of the whole system. If we replace x with the estimated x height, right? In the past 4 weeks, right? In that design, u equals minus kx. X is refers to the state vector, right? Original state vector, but now we are going to use the estimated x height, right? Replace x. Then we want to know what is the effect. Will the whole system still stable, right? Eventually, okay. Let's do some analysis. Okay. All right. So here is the whole plot diagram for our system, right, with the controller and the observer. So without the observer, we know that we're supposed to use this, this kx, right? That will be the state feedback control, right? But we don't know where, we don't have this signal, right? We don't have the signal. That's why this is observer. This observer, right, has the copy of the original system, but with some feedback, right, from the output. Okay, and then for this observer, right, the x height is the estimated state, so we're going to use this instead of x, right? In original design, we use x, but we know x is not available. So the final design, right, we use k times x height in the controller. Okay. But we want to know how does that affect the whole system. Okay. So this is the observer control system, right? So this is the original system. Okay, now we build observer. So in the observer, of course, we're using the original equation, but then we also add the feedback mechanism, right? This is critical for it to work. So with the help of the feedback, doesn't matter whether the A is stable or not, right? We can make sure that the estimation error will go to 0. Okay, how about the control law? So the control law originally is minus kx plus r. Just to simplify the analysis, we don't use fr, we just use r, okay? So minus kx, now we use x height to replace x. And then we want to know the stability of the whole system. Okay, then we have to put the equations together. So let's analyze the dynamics of the closed loop. So we have to plug in the equation of the input into the system. So this is what we have: x dot equals ax plus bu, but u is r minus kx height. Okay, now in the next step, we are going to use the estimation error x tilde. Okay, the equation for x tilde. So for that purpose, so let's replace x height by express x height in terms of x and x tilde. Okay. Why? Because x tilde is x minus x height, so x height equals x minus x tilde. Okay, let's plug it in. So therefore, then we have an equation of x dot, right, equals a minus bkx plus bk times x tilde plus br. Now you can see if x tilde is 0, if the estimation is 0, this actually a minus bkx, that is original equation with the state feedback, right? Okay, now we have an extra term x tilde. Okay, but we also know the equation for the x tilde. X tilde, previously we already derived that. This is the equation for x tilde. Change rate will be governed by A minus LC. A minus LC will be stable. Let's put the two equations together. Right, this is the equation for x dot. This is the equation for x tilde dot. Okay, and that is the equation we are going to analyze. So we want to know whether the system is stable. Okay, to get the solution, right, the simple way, because it's a linear system, right, the simple way to get the solution is by Laplace transform. Now, let's do the Laplace transform. The first one is for the Laplace transform of the equation for x dot, right? So therefore, this, because x dot, so we have s times x minus x0, the a minus bk times x plus bk times x tilde plus br. Now, x tilde dot only depends upon x tilde, right? So x tilde dot is Laplace transform is s, x minus the initial condition equals a minus LC times x tilde. Then, of course, the output is simple. Y equals c times x. Then let's try to solve for x, the state vector from this equation. We put this one on the left side, put x0 on the right side. That's how we have this equation. Then this second equation also will put this x on the left side and x tilde 0 on the right side here. Okay, and then we can get the solution in the S domain. We just multiply both sides by the inverse of this matrix, right? We get this solution for x is the inverse of Si minus A plus Bk times x0, and also the inverse of this matrix, right? Times, because x tilde, remember x tilde is here, x tilde is, we do the inverse of this matrix times x tilde 0, right? We put in this corresponding to x tilde s. Okay, and then we have another term. This one is contribution from the reference signal R. So this is the expression of the x in the S domain. The y is simple, right? Y is just c times x. Okay. So let's just look at the expression of the x, right? It depends upon the initial state, right? Depends upon the reference input, and depends upon the estimation error. We know the closed loop poles, right, will be the eigenvalues of A minus Bk and A minus LC, right? A minus Bk and A. So as long as those two matrices are stable, then we know, okay, this one, right, this term will go to 0. Of course, we're going to design, right, a K to make A minus Bk stable, right? Also place the poles of A minus Bk to the desired ones. And also we design the L to make the poles of A minus LC, right? The poles to be stable. Now, if we look at the transfer function from the R to X, that is here, this one, the transfer function keeps the same. Okay. Sorry. Okay. Now you can see there's some extra term like contributed by the estimation error here. So if there is no estimation error, right, those two terms will correspond to the original system, right, where you have the state feedback, right? If you don't use the observer to estimate the state variable, so those two terms correspond to the solution of the x, well, with only the state feedback. Now, with the estimated state, right, we have this extra term contributed by the estimation error. So if there's no such term, of course, the performance will be the same as the one with the purely state feedback. But because of this, we know, okay, the errors in the initial state estimation will propagate through the feedback loop until this whole effect will go to zero, right? But we know it will go to zero if we look at this, right? The Laplace transform, we know the poles will be contributed by those two matrices, right? And we know the poles are stable. So the whole term of this one will go to zero. Therefore, the difference, right, the error x with and without observer is just this term. The inverse of this matrix, right, and times pk of the inverse of this matrix. This correspond to the closed loop control system, right? This corresponded to the observer, right? A minus LC. Okay, now clearly, right, whole system is stable as long as, right, this A minus pk is stable, A minus LC are stable. Okay, there is no question about that. Let's look at one example. Okay, we want to say a difference between the system if we use the original state feedback or use the estimated, right, state feedback. So, okay, this is the system, right? To simplify the discussion, we just use the first order system. We want the state go to zero, so the reference signal is zero. The initial state is one. If we use the true state feedback, let's see what happens. Okay, we use up because remember, so this original open loop is unstable, right? Unstable, you have a pole of two. We have to use feedback to stabilize it. So a simple one just use minus u equals minus 2x. Then we get a minus 3 times u, right? Minus 6x, right? The closed loop will be 2 minus 6, that will be minus 4. A minus b will be minus 4. Then easily you can get the solution. The solution is e to the minus 4 t, right? E to the minus 4 t. The initial condition is 1. Okay. So this one is simple. Now let's say what happens if we use observer, right? Okay. If we use the observer, so this is the observer. Then we just choose our design with L equals 10. The observer pole will be minus 8. Then the control law. The original control law is minus 2x, right? So we're going to use minus 2x height. And the initial state of the estimated state variable, because we don't know the value, right, of the true value, we just assume it is 0. Okay, then we get, okay, the initial state estimation will be 0. Then the difference between those two cases, we have the formula, we can compute. Okay. This is the Laplace transform of this difference of those two cases. We can easily get because we have s plus 4, we have s plus 8, right? So this one, s plus 4, that corresponding to e to the minus 4t. This here is plus 8, that corresponding to e to the minus 8t. Then the output with observer, right, will be this difference and plus the original one, right? This one plus the original output. So this will be the output if we use the observer. And then we can see the difference. This is the one, the solid line, that's the one with the original state feedback. This one is the estimated, right? We use the estimated state to replace the original state. So you can imagine, of course, at the beginning, right, there is some difference because the estimation error is not 0. But eventually, we know that error contributed by the estimation, right? That part will go to 0. So you say after a while, right? So here, that's, like at around 1.6, you can say already there is no difference, right? Both of them go to 0. Okay. So from this one, I just want to assure you that, right, if you design the control system properly, and then if you design your observer properly, then you combine those two, the performance will be similar as the one with the true state feedback. You're going to observe some difference, right? You're going to observe some difference at the beginning. But if you look at the steady state, of course, we know at the steady state, when time goes to infinity, there's no difference between those two. Okay? Any questions? All right. Now, let's come to the final part of this observer design. There is one question we already mentioned, right? In the previous observer design examples, we noticed that some state variables are actually already available from an output. Can we reduce the redundancy, right? This is example we already solved. We design observer to estimate both x1 and x2, but x1 corresponds to the output. So there is no need to estimate x1. So we only need to estimate x2. Okay, so that is the issue we want to resolve, right? We want to reduce the order of the observer because we don't need to estimate all the state variables. Some of them may be already available from the information from the output. Okay, so this is the motivation. So we look at the output, y equals cx. Let's say there are m outputs already. The dimension of the state is n. Of course, m is smaller than n, right? So n, and we also suppose, right, c, the output matrix C, right, has a rank of m, so which means those outputs are independent from each other. Okay, then we want to take advantage of this m output signals. We know they will correspond to m state variables. Okay, now, of course, we say they may not correspond to original state variables, but remember, right, we can transform the state variables, right? That many kinds of transformation, right? And then we can use the output to construct some of the state variables, m of them. But of course, then there are some other ones are missing from, right? There are remaining n minus m. So the output, the m outputs, so there can provide you m state variables, but there are some missing ones, n minus m. But the motivation is Okay, since we already know those m output signals, we want to use them, right? And we only need to estimate the remaining n minus m variables. So like the case in the previous design, right, we have two state variables, x1 and x2. We don't need to estimate both of them because x2 is already available through the output. Okay, so for that purpose, let's say let remaining, right? We already know m output signals, right? With the remaining n minus m state variables, we say we use cassia to denote those remaining ones. But cassia, of course, is not x, right? It's the remaining ones. So therefore, we say cassia equals t times x. T is the matrix, and we know the dimension of the cassia is m minus m. Okay, so therefore, this matrix T, the dimension there are n minus m rows, right? Times n, because we are only interested in n minus m state variables. Okay. Now let's put those output and the C together. The output and C, the output there are m of them. C there is n minus m. I will put those two together. That will be n-dimensional n variables, and we know they are related to the state vector, the original state vector. So we know y equals c times x, right? C equals t times x. Okay. Now there is an important condition on this matrix CT. This matrix CT, this is a square matrix with a dimension of m by n, and we want to be a non-singular matrix. Okay. Only a non-singular matrix is qualified to be a transformation matrix, right? You transform the one state variable and it can be transformed back. Okay, so this matrix CT square matrix has to be non-singular. Is that clear? Okay, now, all right. Then the problem becomes, right, we already know y, right? We want to know C, but C equals t times x. We want to estimate the transformed state variables instead of the original one. The original one is x, but now we want to estimate t times x. And you may wonder, how do we transform the state, right? You say there are infinite number of ways to transform the states. So that actually provide us with a lot of freedom to design. So we are going to use this to our advantage. I'm going to show you that later. This transformation T will be the design variable in the reduced order observer. Okay. All right. So once you have this output and also the C, right? Because this matrix is invertible, right? We can construct the original state vector by this equation. Okay, so that is the idea. Now from this equation, easily you can say, of course, X is a linear combination of the output and the observer's output C. In general, if the dimension of the state variables is n, if there are m outputs, so we only need to estimate m minus m state variables. Okay. Now let's see how we're going to construct observer. Let's do it step by step. First, we consider the system. Right? This is the original model. But remember what we did for the full order observer. For that observer, right, what we did is we used the original equation, right, just plus An extra term, right? An extra term. Right? We construct the observer in this way. Right? And then we say, okay, we can design error to make A minus LC stable. Now think about the observer for the reduced order one. Can we also directly use the original model as a part for our observer? Can we still use ABC as a part of the observer? What do we try to estimate? Do we try to estimate X? We don't try to estimate X, right? We try to estimate T times X, right? So therefore, the model of the observer has to be constructed because we are not going to estimate X directly, we are going to estimate T times X, the transformed state. That makes a difference. So we need to design the observer from scratch, so we cannot use ABC directly, right? Because we are not going to estimate X directly, we are going to estimate T times X. That will be the main difference between the full order observer and the reduced order observer. And also the design of the full order observer is simpler than the reduced order, right? The design. But eventually, of course, the calculation of the reduced order will be simpler than the full order one because the order of the observer is reduced. All right, let's see how we're going to do that. This is the equation for the original system. We want to construct observer, right? Observer. We know this observer, of course, will depend upon the input, will depend upon the output. Of course, this C, right, will depend upon itself. That will be the general form for any observer. But we can no longer use ABC because we're not going to estimate X directly. We use C. C corresponds to T times X. So what's the objective? We want this C converge to T times X when time goes to infinity. So we keep in mind that. So that is the objective. And then we try to design the observer such that the difference between C and Tx will go to 0. So, of course, we have to analyze the dynamics of the estimation error, right? So, therefore, we define the estimation error as C times T times X. Okay. Then we want to construct the observer such that this estimation error will go to 0 as T goes to infinity. It's the same goal as that for the original full-order system, right? Is that one we say, okay, we want to make the estimate X height minus X, right? We want to estimate X directly. Here, instead of estimating X, we're estimating T times X. Okay, we keep in mind this goal, right? We want to make this estimation error go to 0. Then we see what we can do to design those gains in that equation. So let's write down the equations for the error. So we want to get the equation for the E dot, right? The rate change rate of the estimation error, of course, is the C dot minus T times X dot. But this one, okay, we have the equation for the observer, right? C dot equals D times C plus E times U plus G times Y. X dot is just AX plus BU, right? Of course, we know T times X dot. This is the equation for that. Then we get the equation for the estimation error. Okay. The equation, of course, looks more complicated, right, than the original 4-order observer, right? That equation is quite simple, but here it involves a number of design variables. Okay, but remember, D, while we're going to design the D, we're going to design the E, right? We're going to design the G. In the reduced order observer, right, we only need to design the G, the gain for the output. Okay, here, this is the equation. Okay, so what's next? Remember, so what we're interested, right, is the error signal, E. If we look at the right side of this equation, right, it involves C, it involves X. But what we're interested in is E, right? So we want to make those E appear on the right side. So what should we do? We have this equation, right? So we're going to replace C by E and Tx. Because E equals C minus Tx, of course, C equals E plus T times X. And we plug it into this equation. Okay, we replace C by E plus Tx. And we regroup all the signals, right? So one part corresponds to E, T times E, right? There are signals related to X, we group them together, T times T, okay, minus T times A plus T times C. Those are the gains for X, and then there are some signals related to the input U, right, is E minus T times B. Okay, so that will be the equation we're going to focus on. The objective, we want to make the E go to 0. Okay? And we want to design, what are the design variables? D we can design, right? T, that's the transformation matrix we can design. Of course, A we cannot change. A, B, C are a given. G we can design. Okay, so you see we have a lot of freedom. First of all, let's talk about D. Okay, so how do we design D? We want to make E go to 0. So what kind of D should we put? D has to be, can we put D equals 0? Remember, if you put D equals 0, you eventually get something E dot equals 0, right? E will not go to 0. So what is condition on D such that we can make E dot go to 0? Okay, if it's a scalar, it is negative. Of course, just say the D has to be, remember, the E could be a vector, right? So D has to be stable. A stable matrix D will be good enough. Is that clear? So you can just imagine, okay, this one looks complicated, but let's say, okay, I put everything here. Of course, it involves X, it involves U, but I just put this as V, right? Therefore, you have an equation like plus V. Now, objective, I want to make E go to 0, right? So remember, E is a vector, so D has to be stable, right? T cannot be unstable. Unstable will not make E go to 0. So D is stable, okay? So we can choose the stable D, right? But look at this one. D is stable, is not enough to make E go to 0, right? We have to deal with this extra term. Those whole thing has to be, imagine, right? You have a stable system, but you have some input. How do you make the output 0? The input, you have to make it to be 0. Otherwise, the input will induce some output, right? It means, can we make this whole thing a v equals 0? Then you can say, you cannot control x and u, right? X are the state variables, the input variables, you cannot make them to go to be 0, right? They are from the system. So what you can do is you design your D, right? T, G to make those gain to be 0. Is that clear? So therefore, eventually what else do we want is, okay, I make D to be 0. I'm sorry, I make D to be stable, but I make those two terms disappear, which means I make those dt minus ta plus tc equals 0 and e minus tb equals 0. If we can make those two equations to be 0, so finally what we have is just E dot equals D times E. Okay, so if we have this kind of equation, and we know as long as D is stable, E will go to 0. Is that clear? So once again, from this equation, clearly you can say you cannot choose 0D. If you choose 0D, your E dot equals 0. E dot equals 0 means E will be a constant, right? That's not what you want, okay? All right. So therefore, those are the two design equations, right? We want to solve. Then, so how are we going to do that? So natural way seems to, we want to choose the transformation T first, right? And then we design the D, we design the G, we design the E. But it turns out what we should do is that we should design the stable D first, and then we design T and G from the main design equation, right? This will be the main design equation. Okay. Okay. So here I first give you a summary of the design procedure. Okay, you find some conditions on the transformation T. Remember on this whole matrix, the square matrix has to be non-singular, right? If it's not singular, if it's singular, then that cannot be a transformation matrix, right? But we do not choose T directly at this step. Using the freedom to design the transformation matrix, actually that will be the key to success. All right, how are we going to design D? We know that D has to be stable, okay? Which means all the eigenvalues have to have negative real parts. And then, so once you design your D, you try to solve this equation, dt minus ta plus tc equals 0. This equation, you already know D, right? You know A, you know C, you are going to solve for T and G. So once you have this T, right, and also how do you get the E is simple on this equation for E. It's just T times B. So you can say, okay, the step 2 and step 3 are the key steps because the final step is trivial, right? and this will be the main design equation. Okay, so once you have constructed the reduced order observer, don't forget the last step. In the last step, you have to show how you get the original state estimation, right? So basically, you have this output, you have the estimate C. This is the transformation matrix, right? You get the inverse of that transformation matrix times this one, you get the estimated state. And that will be the state you can use for your state feedback control. All right, so we're going to go through two design examples. Okay, first, simple one. This is the system. We know it's a second order system, right? We have output. We already have one output. Actually, if you look at this one, this output corresponds to x1, right? Y equals x1. Remember, this is the example we have already studied before. So now we want to design a reduced order. Then only x2 needs to be reconstructed because we already know x1. Okay. Then we know, okay, the observer, this is the form of the observer. And we know because there is only one state variable for us to estimate those. Kc will be a one-dimensional vector, right? So Kc is a scalar. If Kc is a scalar, so of course D will be a number, a scalar. How about E? Because we know there is only one input, right? The U is a scalar, so E will be a scalar. Okay, because the output Y is a scalar, we know G is also a scalar. Okay, so that will make it simple. Okay, now the first step, we need to find out the constraint on the transformation T, right? But we know, of course, T is a row vector because there is only one state variable to estimate, so it's just a one row, but it's a second order system, so it involves T1 and T2, such that, right, this matrix, right, say T, C is 1, 0, so therefore T, of course, will be just T1, T2. This is a square matrix, and this matrix has to be non-singular. Okay, and easily you can say how to make it non-singular. As long as T2 is not 0, right? T2 is not 0. Okay. Then the second step, you choose a stable pole, right? So D equals -3. Of course, you can choose -1 or -2, but you should never choose +1. Then you design T and G from this main design equation. Essentially, right, what should you do? You just plug in the expression of all the design variables, right? We write this equation as TA minus dt equals, right, G times C, right? This is T, T1, T2. This is A matrix, we already know. Now this D is already given, right? -3, that's why I have +3 times T1, T2. G is a design variable, and C is given 1, 0. So you compute the equations on the two sides, right? We get this one, right? We get, right, this row times this matrix, we get 0, and T1. This is just 3T1, 3T2, and this is G0. So finally, we compare from this equation, right? If we want to match, we have to match those two elements. So we get 0 plus 3T1 equals G, G equals 3T1, and the second one, T1 plus 3T2 equals 0. Okay, so from this design equation, we end up with two equations. But look at those two equations. How many solutions can you get? You can say, okay, there are two equations, then how many design variables? How many design variables? 3, right? So how many solutions can you get? You have more design variables than the number of equations. So you will get infinite number of solutions, right? Okay. But before we get the solution, let's look at another way, right? Let's look at another way. Like I said, right, I already mentioned the most natural way, of course, actually is that T, because in this problem, we know T is a matrix to make this non-singular. But for this problem, we know the first state variable, right, is x1 is available from the output. So the natural choice we say, okay, T2 is not 0. So why don't we just T as T2 equals 1, T1 equals 0, right? In this way, we know, okay, the estimated C actually will correspond to state variable x2 directly. That is a very simple thinking, right? Also a very direct way. So why did we do it? Okay, here, let's say what would happen if we do it this way, which means, right, we design the T first, and we choose the simplest design of T. Okay, so we already fixed T. T is 0, 1. Now, then let's design the D and the G from this equation. Okay, now we plug it in. So rewrite this equation as TA minus D times T equals GC, right? Okay, now this T is already fixed, 0, 1. A is given 0, 1, 0. D, we can design. T is 0, 1, and the G of times C is 1, 0. So on the right side, so this one times this, we get, this is 0, this one also is 0, 0, 0 minus D. Put it in, we get 0, D here equals G, 0. Now you look at this equation. This time, how many solutions can you get? Look at this equation. How many solutions can you get? What is D and what is G? Both of them has to be 0. Or we say, hey, it's simple, right? We only get one solution. But look at this solution. Can we this solution for our observer design? What is the problem? Do you have a problem with G? Do you have a problem with D? Do you see the problem? D is 0. Is that a stable? We cannot put a 0. D cannot be 0. D has to be negative value, right? You see? Yes, you follow the simplest design, but turns out it doesn't work, right? So that is the reason, right? You don't choose T at the beginning, although you follow some very simple idea. It turns out, right? It turns out you'd better not do that. Okay. Okay, now, so from this, we say we cannot choose T by the most natural way. Okay, with the better design T from the equation. We cannot fix T in a very simple way. So that is the very important lesson. Is we have to design T. Actually, that gives us the freedom to meet the equation. Okay, now let's go back to the original two equations we have, right? If we don't fix T, right, then we have two equations, but we have 3 design variables. Okay, we know how we're going to do it. So this one is simple. Whenever you have this kind of problem, you can just choose any solution which can satisfy those equations. Simple one. You have 3 design, right? You have 2 equations, you just fix one of them. pick anything. For example, you put G as 1, simple choice. Then you have two equations, right? You get T1, T2. Of course, you know, okay, this one, T2 cannot be 0, right? Remember, that is condition. So you pick G as 1, right? Then you get T1 and T2. The other way, you say, okay, yeah, you know, I know T2 cannot be 0, so I can fix T2 equals 1, right? There are infinite number of possibilities. You just pick any way you like. Just remember T2 cannot be 0. So that is the requirement. So in this way, we say we try G equals 1, we get T1, T2. Now you have two equations. You get two solutions, T1, T2. Once you get T1 and T2, you can compute your E. Okay, T times B, right? You already have T1, T2. You get this E. Then you get all the numbers for your observer. I can see for this is T is -3, right? This is E. You have, you know, is minus 1 over line. Now this is G. The gain for the output is 1. Okay, so that finishes the design for your observer. But finally, right, we can don't forget this last step. If you have this is a question like this, right? Sometimes students thought, right, I already finished the design, but okay, you'd better show me how you're going to get the original state. Sure, okay, so okay, this transformation matrix, you do the inverse of that, right? You have this see in this way you can reconstruct the original state. All right, any questions? Okay, so here is the block diagram for you to show you how you construct that, right, in the simulink. Okay, the next way let's go through a little bit more complicated example. Right here, we have two outputs, but then there's a third order system. And of course, we can check the observability matrix. We know it's 4 order, so it's observable. But first of all, since we have 3 state variables and we have 2 outputs already, so how many state variables do we need to estimate? 1, 2, 3. How many? We already have 2, right? How many? We only need to estimate 1. Good. So that still will simplify, right? We already have 2. The dimension of the state is 3. 3 minus 2. Okay. So still is a first order observer. C dot equals D. C plus E times U plus G times Y. But remember, right? C is scalar. Okay. So therefore, D. Is D a vector or scalar? Look at the equation. C is a scalar, right? So therefore, D has to be a scalar, right? How about the E? We look at the input. Input is a scalar, so therefore E is also a scalar. Then how about the G? But now the output Y is a vector. G times Y should be a scalar. So therefore G has to be a scalar or vector. Has to be a vector, right? Otherwise you cannot get a scalar. So D and E are scalar, and you know G has to be a 2-dimensional vector. Okay? So you need to know that. Okay. All right. Then how about T? Of course, with T is our 1 row, but it's a 3 by 3 matrix. We know, okay, it has 3 design variables are T1, T2, T3. Because the C T, this whole matrix, transformation matrix, right? You put in this is C 1 0 0 1 1 0 T1, T2, T3. This whole matrix has to be non-singular, right? Okay. we say, okay, the rank of that matrix has to be 3. So therefore, that gives you a condition on T3 cannot be 0. Now, okay, then we choose the eigenvalue of the observer. So here, right, just for simplicity, right, you can choose -1, -3, but here I choose -2. Like I said, it's up to you. If you encounter a situation, let's say similar problem, right, you can just choose any number you like. You want to choose some simple number to simplify your calculation. Okay, so once you have the D, and then we have to find out the T and G from this equation. So how are we going to do that? You just plug in the design variables into this equation, and then you will find out the individual equations. So this is T. T is this row vector, right? A is given 3 by 3 matrix. This is D. D is one number, actually is already given, -2, right? This T1, T2, T3. G is G1, G2. A row vector right here is the C. Okay, and then you multiply this vector and this matrix. Okay, you are going to get a T3, T1, T2. Okay, and this one, or T is -2, right? Plug in, so it's just +2. And then this one, you do this multiplication, you get G1 plus G2, right? And then this corresponds to G2. And finally, this one will be 0. So I say, from this equation, you can say we're going to match 3 elements, right? Therefore, you are going to get 3 equations. Now, you have 3 equations, but how many design variables? How many design variables? We have 5, right? T1, T2, T3, G1, G2. Therefore, easily you can say how many solutions you can find. Again, infinite number of solutions, right? You just pick any simple numbers you like, right? You fix 2 of them. Okay, for simplicity, I just fix G1 and G2 because remember G1 and G2 are the gains in the observer. I'll fix some integers. From that one, you get your T1, T2, T3, and of course, the important number is T3. T3 cannot be 0. So the other numbers, right? Doesn't matter whether T1, T2 are 0 or not, but T3 cannot be 0. But anyway, you just fix. You have 3 equations. You have 5 design variables. To get a solution, you just fix 2 of them, right? And get the other 3. Okay, then T you already have, right? Then you compute your E. E is just T times B. This will be the observer. Okay. All right. Any questions? Okay. So finally, right, like I said, you have to show the last step. Show me that how you reconstruct the original state. Right. You have to do the inverse of this transformation matrix times the output and the estimated C. Right. You do this inverse, you get that. Okay. Say, hey, you can use this transformation to reconstruct the state. Okay, and then here I just show you the block diagram for you to build in the Simulink. Okay, finally, let's talk about we talk about the reduced order and how is this reduced order observer related to the 4 order observer. Okay, for you to see that, we know that the 4 order observer, which means we are not going to use any of the output information, right? We are going to use the estimate the whole state vector. So That is a very special case where the T actually is an identity matrix. So the estimated state variable corresponds to the original state, which means C equals Tx. T is identity matrix. Okay, and then let's look at the design equations for the reduced order. If T is an identity matrix, what we have is D is A minus G times C. Then the eigenvalues of this D, we know, okay, because we know the final equation is E dot equals D times E, right? So D, that is the matrix controlling the decay rate of the estimation error. The eigenvalues of D, of course, have to be stable or have the negative real parts. A and C are given. Then the matrix G is the design variable, right, which you can use to make this new matrix A minus G times C to be stable. But remember, of course, originally we use air. This G corresponds to air in the full order observer. Can you see that, right? If we assume that T is the identity matrix, this reduced order observer actually becomes this observer, and this is the full order observer, right? Where actually G corresponding to air if we use our original notation. Okay, so which means actually the full order observer is kind of a special case of the reduced order observer. Okay, is that clear? Any questions? Okay, so if we force the T to be identity matrix, right, then actually the full order observer is the reduced order observer. Okay, now let's summarize. We have what we have discussed today is about the state estimation. The reason is that we want to save money, right? We don't have the sensors to measure all the state variables because the state variables are related to each other, right? We have the model with that information, and then with the correct feedback mechanism, right, we can estimate the state variables from the input and output. Okay, subability. So there is a condition. I would say the system has to be, right, observable. And then we discuss two methods, right, to design the observer. You either use the full order observer or the reduced order observer. Let's say if you have a question, right, if there's no requirement whether you should try a full order or reduced order, that is up to you, which way you like. It's up to you. But if it's explicitly required, you have to use the full order, or require you should use the reduced order, okay, then you have to follow the way. The same rule applies to other questions, like, you know, for pole placement. If I ask you to do a pole placement, you know, I give you the desired poles. If I didn't say, hey, you have to use the full rank method, then any method you can do, you can use. But if you're required to use one of the methods, you have to follow the instruction clearly. And also I show you the stability proof, right? We say, okay, you can design the state feedback controller, make the whole system stable. And then you design a stable observer, right, to make the estimation error go to 0. You combine those two, you are guaranteed that the whole system will be stable. All right, now when you design your control system with state space model, like what you are doing with the mini project, you can always follow the following design procedure. The first one, you always assume that the state variables are available. Okay. Even though in reality they may not be available, but that is not a problem because later you are going to resolve that, right? You first try to get the solution, assuming that everything is available. Then you build a state feedback controller. You don't have to worry whether you can afford to buy the sensors. You make sure, so if you have all the state variables, can you solve the problem, right? Imagine if you have all the information and then you cannot solve the problem. So you forget about it, you don't even move on to say, if only partial information is available, can I solve the problem? Of course you cannot, right? I give you everything you cannot solve. And then I can only give you half of the information. How can it be possible for you to solve the problem, right? So step one, you need to finish that, right? That also corresponds to the question one, question two of your mini project. You assume that all the state variables are available. You design the state feedback control. Then step two, right? Then you decide, right, what kind of sensor you want to buy to implement your controller, right? So that will, right? This one, of course, it will depends upon the budget, right? Whether if you are rich enough, you can buy, probably can buy all the sensors, right? But remember, right? Actually, you don't want to waste your money, right? You want to save the cost, even though you are rich. Okay, so but that will be compromised. We know, of course, if you have all the state variables available, the performance will be a little bit better than the one without, right, the sensors. Okay, but if sometimes, if cost is real critical, you want to save money, right, then you just use the cheapest sensor, right, to measure one state variable, right, which means you measure one output. Then you may wonder, hey, I'm really poor, I cannot measure any output. So can you solve the problem without any output information? Which means, right, there is no feedback. If there is no output, there is no feedback, right? Therefore, you cannot. So that's very dangerous if there is no feedback. So at least you have to get one output. Okay. Then step three, of course, as long as the system is observable, right, even with just one output, you can estimate all the state variables. Of course, there are a number of assumptions. One big assumption is that your model is accurate. Your model is accurate enough. If your model is wrong, of course, your estimation will be totally wrong. Then with this information, I think now you're ready to complete the whole mini project. Okay. Like I said, this will be the end of all the new knowledge you are going to learn from this course. But we are going to have one more class next week. So next week is a revision, revision of all the subjects you have learned, and also I will do a brief on the mini project. But now for those of you who haven't started on the working on the mini project, it's already too late. Okay, you have to start working on it now. Thank you. Yes. A question about the whole placement. If it is better to use a different course or the same course, like the examples in the lecture. I noticed that I need to use two repeated